Hello everyone, my name is T.V. Kumar and I am from Sri Venkateswara College of Engineering, Civil Department. Today we'll be discussing the derivation for continuity equation in Cartesian coordinate and the derivation for Bernoulli's equation. So let's begin. Here is some introduction for the continuity equation. The continuity equation in fluid dynamics describes that in any steady process, the rate at which the mass leaves the system is equal to the rate at which the mass enters the system. When can the continuity equation be used? And the continuity equation be applied in all fluids, compressible and non-compressible, Newtonian and non-Newtonian fluids. Now let's get into the derivation for continuity equation in Cartesian coordinates. Consider a fluid element of lengths dx, dy and dz in x, y and z axis, and let u, v and w be the velocity in this direction respectively. The mass entering the fluid element ABCD will be equal to density into area of ABCD into the velocity in x directions. The density in the fluid element ABCD is rho and the area of ABCD is dy into dx and the velocity in x direction is u. Now the mass leaving the fluid phase EFGH per second will be rho into u into dy into dx plus del by del x into rho u dy dx. The net gain in x direction will be equal to the mass of fluid entering the phase ABCD per second minus the mass of EFGH leaving the fluid elements per second. Here rho u dy and dz minus rho u dy dz will get cancelled out. Then the net gain in x direction will be minus del by del x rho u into dx dy dz. Similarly, the net gain in y direction will be minus del by del y into rho v into dx dy dz. The net gain in x direction will be minus rho by del x into rho w into dx dy dz. Total gain of mass fluid will be equal to the net gain in x direction plus net gain in y direction plus the net gain in z direction. That will be minus del by del x of rho u into dx dy dz minus del by del y of rho v into dx minus dy into dz minus del by del z of rho w into dx dy dz. Now after simplification we can common out dx dy dz, which leaves us rho by rho x into rho u plus del by del y into rho v plus del by del x into rho w. Now since mass is neither created and nor can be destroyed in a fluid element, the increase of mass per unit area per unit time in the fluid must be equal to the increase of mass in the fluid element. But this means that the mass of fluid element in the direction P into del x del y del z and it in rate of increase with time will be given as del by del t into P into dx dy dz. Thus which gives us rho del rho into del t into dx dy dz. Now equating the both equations we get del by del x into rho u plus del by del y into rho v plus del by del z into rho w into dx dy dz, which is equal to del rho by del t into dx dy dz. Now on cancelling dx dy dz and on both sides, after simplification of the above equation, we get del by del x into rho u plus del by del y into rho v plus del by del z into rho w plus del by del t by is equal to 0. This above equation is called the continuity equation for Cartesian coordinates. Now we need to also find out the continuity equation for steady flow. And for steady flow, we note that the mass of fluid with increasing time is always constant. So therefore, del by del t is equal to 0. So the above equation becomes del by del x into rho u plus del by del y into rho v plus del by del z into rho w is equal to 0. Now we by taking density common, del u by del x plus del v by del y plus del w by del z is equal to 0. On further simplification, we get del u by del x plus del v by del y plus del w by del z. Now this above equation is for the continuity flow in 3 dimensions. in x, y and z axis. For two-dimensional flow, the component w is equal to 0. Therefore, we get del u by del x plus del v by del z is equal to 0. So moving on to the next derivation. So our next topic is the derivation of Bernoulli's equation, or even known as Euler's equation of motion. Now sir, let's get some introduction for this topic. The Bernoulli's principle can be derived from the principle of conservation of energy. This states that in a steady flow, the sum of all forms of energy in a fluid is the same at all points that are free of viscous forces. This requires that the sum of kinetic energy, potential energy, and the internal energy remains constant. So let's of Bernoulli's equation. Consider a streamline in which flow is taking place in the direction of S shown in the figure. Consider a cylindrical element of cross section dA and ds. The forces acting in the cylindrical element are the pressure force Pa into Pz in the direction of x-axis and the pressure force P plus dP by ds into ds by dA in the opposite flow of x direction, and the weight of the element P into G into dA into ds. Let theta be the angle between the direction of flow and the line of action of the weight element. Now the resultant force of the element is given by the mass of fluid into acceleration in the direction of s of the element, which implies dp into dA minus rho g dA ds cos theta minus p plus dp by ds into ds dA is equal to p d p into dA into ds into as, where as is the acceleration in the direction of s, which is given by as is equal to v into del v by del x. Moving on to the next slide. And further simplification of the above equation, we get P dA minus rho g dA ds cos theta minus P dA minus del P by del S into ds into dA is equal to rho dA ds into V into del V by del X. Now P dA and minus P dA gets cancelled. So therefore we get minus rho g dA ds cos theta minus del P by del S into ds dA, which is equal to rho dA ds into V into del V by del Z. Now by dividing rho dA ds on both sides, we get minus g cos theta minus 1 by rho into del P by del S is equal to V into del P by del S. Now taking all the terms on the same side, we get g cos theta plus 1 by rho into del P by del S plus V into del V by del Z is equal to 0. Now from the figure B, we know that cos theta is equal to del Z by del X. Now by substituting this equation in the above equation, we get g into del Z by del S plus 1 by rho into del P by del S plus 1 by V into del V by del Z. Now by dividing del Z del S on both sides, we get del Z are eliminated as both dx and del z are equal. We get g into dz plus del p by rho plus v into dv is equal to 0. You can see here that ds is equal to del z. Now moving on to the last slide. The above equation is known as Euler's equation of motion. The Bernoulli's equation is obtained by integrating the Euler's equation of motion. Now integrating the above equation, we get integral of g dz plus integral of del p by rho plus integral of v dv is equal to constant. Now dividing g on both sides, we cancel g on the first term, which is equal to z plus p by rho g plus v square by 2g is equal to constant. Therefore we get v square by 2g, which is known as kinetic energy per unit or kinetic head. P by rho g is equal to pressure energy per weight or fluid or pressure head. Z is equal to the potential energy per unit fluid of potential head. So thank you everyone for listening to this video and have a good day.